Hi everybody, Cal here with section 12.3, the dot product. Dot product introduces basically one way to multiply two vectors together. I should note here, in terms of language, we will never talk about two vectors A times B or A multiplied by B. We will always talk about A dot B. This is just how mathematicians talk about this sort of thing, and there are other ways to multiply vectors together, and so you need to distinguish between them. We define here at the bottom of page 824 A dot B. It's a pretty easy formula. Multiply the components and then add all the results. It is not really clear from that definition what the dot product quote-unquote means, and we'll get to that. Example 1 gives you an example of finding a couple of dot products, and make sure you understand it. Box 2 here is the algebraic properties of the dot product, and again, these are kind of how you would hope it works. Make sure you understand what those are saying. Now, we'll get into the geometric interpretation here midway through page 825. And the trick here is that the dot product has something to do with the angles between the two vectors involved. And this theorem really tells the whole story. A dot B is the length of A times the length of B times the cosine of the angle between them. You should think about, for two vectors of fixed length, how would the dot product between them change as you vary the angle between the two vectors? One would be a maximum, one would be a minimum, one would be positive, and one would it be negative? These are all good questions. Okay, and the proof comes from the law of cosines, which is kind of interesting. It's not very hard to prove, actually, and worth doing on your own. But the book has the proof here. Okay, in example 2, we have an example of using a dot product to, using information about the vectors to find a dot product, and then example 3, we go the other way. We use the dot product to find the angle between two vectors using this corollary 6. And you'll notice that the corollary, all they've done is they've taken theorem 3 and they've divided both sides of it by the length of A and B. Okay, so at the bottom of page 826, we give you a new word, orthogonal, for an old concept, perpendicular. And so we say that two vectors are perpendicular if the angle between them is a right angle, if it's pi over 2. And so that means if the angle between them is pi over 2, then we have a cosine of pi over 2 in theorem 3. And cosine of pi over 2 is 0. So if these two vectors, A and B, are orthogonal, if they're perpendicular, then A dot B has to be 0. And that gives us box 7 over here on the top of page 827. Example 4 shows how to use the dot product to show the two vectors are perpendicular or orthogonal. You can actually skip this section at the bottom of 827 on direction angles and direction cosines. We'll never really look at that. I mean, read it if you want. It's interesting, but we won't be using that in this class. We'll pick it up here in the middle of 828 with projections. This is a pretty important concept. And, I mean, read the definitions over here. But the important thing here is the pictures. And I urge you to spend a lot of time looking at the picture to the left over here. The book proves above this box how it's getting the formulas it's using, and it comes right from these pictures on the left. And you definitely do need to know these two formulas, the scalar and vector projection of B onto A, both how to find them using the formula and what they mean in the picture. Example 6 gives a numerical example of this. Below that, we get into a short discussion of work. Work is a concept you might have run into before in physics. We skipped over it in Calc 2 if you took that here. And here, the work done is, it's got a really easy formula. The work is force dot distance. So if you've got a force vector and a distance vector, I'm moving along a certain vector by being acted on, by a force in maybe a slightly different direction or whatever. I can calculate the work done just by taking the dot product of the two. And example 7 and 8 show that in action. And there you have it.